everyone. Hello. Welcome to this session. This is a Subdivision I session in SMI. We have two papers in this session. And first, I will introduce myself. I'm Lin Lu from Shandong University, and I'm in China now. So, okay, let me first introduce the first paper in this session. The paper is curve-guided T-spline scanning for surface and solid generation. And the authors are Hongwei Lin and Chuangfeng Hu. Chuangfeng Hu will present this work, and I believe both authors are from Zhejiang University in China. So, Chuangfeng, maybe you can share a screen now.
Okay. Can you hear my voice?
Yeah, it's very good. So you can go ahead to start your talk.
Okay. It's our honor to present my work about curve-guided T-spline scaling for surface and solid generation in Shape Modeling International Conference 2020. This work is authored by Chuanfeng Hu, Jiaming Ai, and supervised by Hongwei Lin from School of Mathematical Science, Zhejiang University. I will show our work from the following 5 aspects. Firstly, the background of surface scaling will be introduced. Secondly, I will explain the proposed T-spline surface scaling method detailedly. Next, the proposed T-spline scaling method is extended to the field of solid modeling. And the experimental results for the skinned surface and solids are presented. At last, we have made some summaries of our work. Surface scaling, also called lofting, which is a process of constructing a surface from a set of given curves, called cross-sections or cross-sectional curves. Generally, the given curves are represented by nerves with independent node vectors or different degrees, which bring some difficulties for the scaling. The scaling methods are mainly classified into 2 categories, including approximation scaling methods and interpolation scaling methods. For the former, the skinned surface will be generated within the error bounds. To ensure the skinned surface can interpolate the given curves, several interpolation scaling methods are developed. For example, degree elevation or node insertion are adopted to generate an interpolating skinned node surface. Due to the incompatible nodes, a problem of control points explosion is caused. To solve the node incompatibility, interpolation T-spline scaling methods are presented. However, the current interpolation T-spline scaling methods cannot guarantee the quality of the skinned surface. There will be some wiggles and creases appearing on the skinned surface. Now let's see the workflow of the T-spline scaling method. The input to the algorithm is a set of ordered B-spline curves. Firstly, the given curves are parameterized by chord length to calculate the parameters in the longitudinal direction. The T-mesh and the initial T-spline surface are constructed. Next, several guiding curves are generated to obtain a visually pleasing shape for the scaling. At the same time, we sample some data points on the guiding curves for fitting. And then the least squares progressive and iterative approximation method and interpolation constraint are performed for the skinned surface until the quality satisfies the requirement. At last, an interpolated T-spline surface with high quality is generated. Here, we introduce some basic theories of T-splines. It is noted that in the basis functions, the weights in the basis functions are all set to 1 in our work. According to the previous work, the T-mesh can be constructed by adding 1 or 2 intermediate cross-sections between the given curves. As shown in the pre-image of T-mesh, the black lines are the given curves and the green lines are the added cross-sections. And the nodes of the added cross-sections can be set by the adjacent curves. To ensure the skin T-spline surface can interpolate the given curves, an interpolation condition is presented. As the interpolation of the curve is affected by 2 adjacent curves, the equation can be rewritten as this formula, where V are the control points of the given curves and W are the control points of the T-mesh. According to the T-mesh construction width, we can deduce 2 equations from the above formula. At last, replacing Vij by Wij in the T-mesh, the skin T-spline surface can interpolate the given curves. To obtain a visually pleasing shape for the skin surface, several guiding curves are constructed. We sample a set of isoperimetric points on the given curves to produce guiding curves. As shown in the 2 pictures, the blacker circles are the isoperimetric points, and the orange curves through the blacker circles are the guiding curves. By solving the linear equations with these two boundary conditions, a cubic B-spline curve interpolating the isoperimetric points can be constructed. To fit the guiding curves for the skin surface, we sample some points for fitting, which preserve the shape of the guiding curves, like that. By fitting to the sample points, the skin T-spline surface can achieve high fairness. We employ the LSPIA methods for data fitting, and the iterative format is presented. Suppose the iteration has been performed for 2 steps, and the 2th T-spline surface is generated. By calculating the difference vector and the adjusting vector, we can obtain the 2 plus 1 T-spline surface. The iteration is terminated until it meets requirements. At the same time, the control points are constrained by the interpolation condition to ensure the skin surface can interpolate the given curves. At last, after several rounds iterative fitting and the interpolation constraint, an interpolated T-spline surface with high quality is generated. We also extend the T-spline skinning method to the field of solid modeling. Similar to the surface skinning method, the workflow of the solid skinning method is presented. Several ordered T-spline surfaces are input to the algorithm, and an interpolated T-spline solid with high quality is generated. In particular, the biggest difference is that an optimization algorithm is added to improve the quality of the solid. To be specific, after sampling data points on the guiding curves, several stitched B-spline solids are constructed, and the optimization algorithm is performed for the stitched B-spline solids. We resemble data points from the optimized B-spline solid as the fitting point. It is noted that a B-spline solid is constructed between 2 given T-spline solid surface, and the adjacent B-spline solids are zero continuous in the common boundary surface. In this study, 2 intermediate cross sections are added between the given cross sections to construct a T-mesh, so that the skin T-spline solid can achieve high quality. Similar to the surface scaling case, we can deduce the interpolation condition for the skin solid. Here we introduce some basic theories of the B-spline solids. The Jacobian determinant can be calculated by this equation, and we defined the different vectors as these equations. We have conclusion that if these different vectors are satisfied this formula, the Jacobian value determinant, the Jacobian determinant of the B-spline solids are all greater than 0. So the objective function of the optimization is developed. Firstly, the fitting precision to the data points can be ensured by this function. Secondly, the validity of the B-spline solid can be improved by the following function. As shown in the picture, 3 cones are constructed by the difference vectors in 3 directions. The Jacobian determinant can be improved by maximizing this formula, which can be done by the 2 ways. The 3 central axes of the cones are as perpendicular to each other as possible, and the angles of the cones are as small as possible. Now I will show some skin results. The 2 results on the left are generated by the previous work, which appear some wiggles or creases, and the other results are generated by our method with different T-mesh construction widths. It is noted that the first 4 results are rendered using a same color map, and the last one is rendered using its own color map. And here, the minimum and maximum mean conventional value of skin surface are listed in this table. The skin surface generated by our method with 2 media sections possess the largest minimum conventional value and the smallest maximum conventional value among the skin surfaces, showing that the surfaces are generated with high quality comparing with others. And here are some solid results. And from this table, we can see after the optimization, the Jacobian value can be improved, which means the quality of the skin T-spline solids is improved. Now, we give some summaries of our work. First, a T-spline scaling method is developed for high-quality surface and solid generation. Secondly, guiding curves are introduced to improve the quality of the skin surface and solids. The last one, LSPI method is employed to ensure the fitting accuracy and the stability of iterations. Okay, my presentation is over here. Thank you for listening.
Thank you for your talk. Thank you. And for the audience, you can directly unmute your microphone, or you can raise your hand in the to raise questions. And also, questions are welcome in the chat box, chat window in the in Zoom. Okay, so maybe I read the first question. The input for this method is you need guided. You need guided the T-spline as the ordered T-spline as the guiding curves, right?
Guiding curves.
Yeah, how to choose the guiding curves, or how to give the guiding curves to guarantee the skinning.
As showing the pictures, we sample some isoperimetric points on the given curves and use the B-spline to construct a B-spline curves that interpolate the isoperimetric point. So compare with other methods, the skin surface can achieve much smarter, can achieve smarter than others. So like that.
Yeah. Maybe I change my question into this way. Are there any constraints on this input? Maybe are there any failure cases for this scanning method? For example, sharp features or this kind of.
Maybe we only consider use the B-spline to fit in the points. We do not to consider the sharp feature and others. So this might be a shortcoming of this method.
Okay, thank you. And these input curves need to be uniformly distributed?
Yeah.
Okay. So are there any questions from the audience? Okay, if no, then thanks for the speaker. Thank you.
Thank you.
And
thank you.
yeah, thank you. Thank you for your talk. So we can, yeah, please. So, okay, thank you. Now we switch to the second talk in this session. The second paper is called Proxy-driven free-form deformation by topology adjustable control lattice. And the authors are Yu Zhezhang, Jianmin Zheng, Yi Cai from NTU, that is Nanyang Technological University. So the first author, Yu Zhezhang, is going to present this work. So please, yeah, please.
Greetings, everyone. I am Zhang Yuzhe from Nanyang Technological University. It's a great pleasure to present our paper entitled Proxy-driven freeform deformation by topology adjustable control lattice in SMI 2020. Yeah. Okay, here is an outline of my presentation. Freeform deformation was proposed decades ago, which is a well-known spatial deformation technique. So this is an interface of FFD in 3D Max. To deform the middle portion of the object, you could impose a 3x3 control lattice. User could manipulate those grids to change the shape. Due to the ability of offering smooth deformation, the simplicity of this mathematical formulation, and no restriction on the representation of the object, so FFD is a very popular tool in practice. However, FFD has two major limitations. The first one is that if a control lattice is set with a large number of control grids, the interface looks very crowded or even messy. As shown in the third figure, this is not only blocks the view of the object to be deformed, but also cause inconvenience for interactive editing of the control points. The second limitation is that after the initial creation of the control lattice, the parameterization of the object is determined, and then the topology of the control lattice is fixed during the subsequent deformation process. This seriously affects the capability of continuous and interactive deformation processes. To overcome the first limitation, 3D Max offers configurable FFT modifier. To conform the lattice to an object, the set value function allows user to set the initial lattice manually. However, this process could be done only at the initial stage, and is also tedious. The conform to shape function is provided to fit the control points to the shape of object automatically. However, this function may not work well for the object with complicated shape. So here are some related works. Roughly, geometric deformation can be classified into surface deformation and spatial deformation. The surface deformation deforms the surface using the differential coordinate that represent the local shape of the surface, such as rigid as possible deformation. While the spatial deformation is an indirect approach that deforms a space, and thus any object contained in the space is deformed accordingly. Sedgwick and Perry first proposed freeform deformation. Since then, extensions have been done in several directions. So the original FFD is global control. To support local control, the original Bezier basis function is replaced by B-spline, by NURBS, by truncate hierarchical B-splines. To make the topology of the control lattice more complicated, some extended FFD was proposed, such as tetrahedron-based lattice, arbitrary volume based on subdivision, and T-grid, so that the control lattice could be shaped without the constraint of parallelepiped. FFD use control points to specify deformation. Another way is direct manipulation. User just specify the deformation on the object. Our work does not focus on direct manipulation, which, however, can be implemented in our framework. But most of the FFD and their extensions suffer the two limitations I just mentioned. So our goal is to improve FFD techniques to overcome these two limitations, so that those software packages using FFD can have an enhanced FFD version. Inspired by the concept of the original spatial deformation cage-based method, we proposed to construct a coarse control cage to enclose the object tightly and then deform the cage to trigger the deformation. So the key concept is parameterization that assigns the local coordinate to any points in the bounded space according to the combination of the vertices of the cage. It was also worth pointing out that our paper does not aim to improve cage-based method, though they do not allow topology change of the cage either. So in this work, we present a flexible freeform deformation method that overcomes the two limitations of many FFD methods. The underlying core techniques here is T-spline volume. T-spline has two properties. First, T-spline has a flexible T-grid structure, which allows us to create a nice proxy. Previous method only used the proxy T-grid to generate a control lattice in complicated structure. So we propose a concept of proxy, which is close to the shape of the object. The proxy could provide a concise and cleaner interface and overcome the first limitation of the cumbersome interface. Secondly, T-spline has local refinement algorithm, which could change the topology without changing the shape. This property makes the topology of lattices and proxy could change. Previous work which applied T-spline to FFD only use the first property, does not use the second property. We make full use of the advantages of T-spline to overcome the fixed topology limitation, so that the topology of the control lattice can be changed during the deformation process. So the novelty lies in that we present a proxy-driven freeform deformation technique with topology adjustable control lattice, while inheriting all the virtues of FFD such as C2 continuous, global, and local modification. Particularly, the user works with a proxy that provide a much concise and intuitive interface, which is easy to use. Our technique allows local topology changes of the proxy after parameterization, which is not available for most FFD method or even cage-based deformation. This actually changed the workflow of the conventional FFD. As shown in this figure, every time when the control lattice performs refinement of the topology, the conventional FFD needs to recalculate the parameterization, which implies starting a new FFD. By contrast, our method permits adjustment of the control lattice both geometrically and topologically without the need of reparameterization. So in the following slides, I will introduce the methodology in detail. Similar with T-spline surface, we define a T-spline volume by T-lattice that is parallelepiped with T-junction. T-junction are the endpoints of partially terminated grid lines. We introduce a class of degree 3x3x3 T-spline volume that is tailored for FFD. The connectivity is hierarchically organized as edge, face, and cell. The equation of the T-spline volume is given here. So given an object to be deformed, we find a bounding box. Assume that the two offset corners of the bounding box have the coordinate min and max. So we generate a parallelepiped for initial control lattice with n control points. To make the exterior faces of the parallelepiped be close to the object, we set the nodes to satisfy the Bézier end conditions. That is, we choose multiple nodes at the two ends and the uniform nodes at the other places. Consequently, the parameter domain for the deformation space is from 0 to 1 by 0 to 1 by 0 to 1. For the geometry of the control points, its Cartesian coordinates are set at their trivial FC. So due to the special setup of the control points, the parameterization has the linear precision property. The parameter coordinate of any points contained in the deformation space can be explicitly obtained by the following equation, which is quite simple and easy to calculate. To simplify the user interface, we choose to leave the corner of those cells intersecting with the object, which are closer to the object and have more influence on deforming the object, while we had the rest of control points. The corner points form a mesh, which we call the proxy. The proxy looks much cleaner, and the proxy served as a deformation handle. The control lattice and the proxy can be refined by locally adding points, which result in local topology change of the proxy. To keep the parameterization of the deformable space unchanged, the refinement is done by T-spline volume local refinement algorithm. Note that the refinement may cause insertion of some extra points or move some existing control points to new locations. The user can select one or more edges, faces, or cells to subdivide. In addition, the proxy will be updated thereafter. In our FFD, we just provide a proxy to user. User could manipulate several points on the proxy to do deformation, but the underlying deformation is calculated by T-spline lattice. The other points which are invisible or held by us should move in an appropriate manner so as to respond to the user's input and make the deformation look natural. So how to change the rest control points of T-lattice? We propose a Proxy-driven volumetric deformation. We construct an optimization function which has 4 terms: target deformed term, surface Laplacian term, volumetric Laplacian term, and one form term. Here is an example to show the capability and the efficiency of the proposed deformation method. So user could select some points to editing the shape. And after that, he could manipulate geometrically and topologically iteratively. So the user interface can switch from the whole lattice and the valid proxy. Yeah. Here we can edit the topology of the control lattice to insert more control points for this region. Also, the proxy-driven deformation could get a good result. Yeah, okay. Here, in this slides, I want to highlight the process of editing the topology and the geometry of the proxy. For the branch part of the pair, we need large deformation. It requires small degree of freedom. We could apply local refinement algorithm in this region to add extra degree of freedom by adding some actual points. After manipulating the deformation, we could refine the topology of other region of interest, similar to level of detail. Previous work did not provide this. That is, after the setup of the initial control lattice, the only freedom that FFD offered to user is the relocation of the control points. Okay, here we compare the user interface of our proposed proxy-driven deformation with Autodesk 3D Max. The initial setup for both methods is a control lattice of dimension 12 by 12 by 12, which gives 1,728 control points. With our method, the proxy is formed by 628 points. It can be seen that the proxy gives much clean user interface and thus facilitates the specification of deformation. Okay, in this experiment, given a cut model, we first construct the T-lattice. Then with the proxy, selecting and moving the control points is also simple. Sometimes the degree of freedom of the control lattice is not enough. We could insert more control points. During the process, the control lattice topology of connected could be changed. Both geometric and topological editing is applied to the proxy. So more example is here. It can be seen that the proxy and the local refinement, with the proxy and the local refinement, various deformation process can be easily and flexibly done. Here shows an application. Sometimes the object to be animated is too complicated. We can define an animation to the control lattice or proxy. The animation of the proxy will be transferred to animate the object embedded. It could achieve the effect of dimension reduction. So in conclusion, we present a solution to overcome the two drawbacks of FFD. It has several nice features. Firstly, it provides a cage-like interface for the user to perform freeform deformation, which avoids manipulating too many control points and achieve easy to use. Secondly, it allows topology change of the control lattice during the deformation process, which is not possible for most FFD method of cage-based deformation as well. Thirdly, it supports continuous and interactive deformation processes. However, the proposed method also has some limitations. it is less flexible to achieve large deformation than cage-based method. Secondly, if we start with a very coarse mesh, it will take time to perform T-spline volume local refinement algorithm to create a dense proxy. Thirdly, our method does not provide limits on the deformation or guarantee on the as rigid as possible minimization procedure to make sure that the computed deformation is valid. Okay, that's all for my presentation. Thank you for listening. Yeah, if you have many questions.
Yeah, thank you for your talk. It's very interesting work, and we already have a question in the chat box. Can you see the question in the chat box?
Okay, I will check.
There is a chat. There is a chat
Okay, yeah.
menu. Mm-hmm.
Okay. For cage-based method, they create a very coarse mesh to embed the object. But for our method, we introduce a T volume, and then the proxy is calculated based on the T lattice. It seems like we can use a proxy directly, but we would not use the T-spline volume in FFD, since FFD is C2 continuous, but cage could only usually got C0, and sometimes you achieve C1 continuous. Yeah.
Okay, thank you.
After the parameterization, we do not need to recalculate that again. So during the process, we just use, we can just directly manipulate the points or edit the topology. Yeah.
I also have a question.
Yeah, and I see another question from Oleg, and also Dominic raised hand, and now please maybe Dominic.
Okay, thank you. Thank you very much for your talk.
Yes.
It was very clear. It's a good point to see and to manipulate less control point, but you still have the full volumic mesh, don't you?
Yeah, we still have the full control lattice underlying there.
What are the drawbacks of that?
Yeah, but actually you cannot see the drawback because we want to fully make use of the T volume that have the property of the flexible T shape and the local refinement property. Yeah, that one is not cannot be achieved by other method. Yeah.
I was also wondering, why did you use T-spline volumes? Rather than, why did you use T-splines volume and not just simple B-splines volumes?
Okay. T-spline can provide two properties. The first one is they can provide a flexible T structure. Then the second one, the most important one, is that it provides a local refinement algorithm so that the topology of the control lattice can be changed during the deformation processes. No need to recalculate the parameterization.
I got the impression that the parameter domain is a grid, a very simple grid anyway. So I don't really see the point on T-spline, but probably I missed something.
Oh yeah, that's yeah. For the detail of the T-spline structure, you can refer to my paper. Just a small, just a very simple illustration here. Yeah.
Yeah, thank you. But I thought you were computing. Oh, so you're not always computing as initial lattice a full parallelepiped grid. Sometimes the initial could be of that shape you are showing.
Yeah, so actually, given an object, we first construct a parallelepiped control lattice. But after that, we just show the proxy to user so that user can manipulate the proxy in a more concise and a cleaner user interface. Then our proxy-driven deformation will map the map the deformation of the proxy to the underlying control lattice. So it's like a proxy-driven volumetric deformation.
Okay, thank you. All that I understood, but
yeah,
okay.
yeah. So only user could only see the proxy, but on the underlying there is a T lattice.
Okay. Thank you. I don't want to monopolize. You have other questions.
Hi, Changfeng. I'd like to also have another question in the chat box. It's also related to user control. Maybe you take several seconds to read it. Can you see it?
Is that one? I just see the difference from the cage-based deformation.
Sorry, can I use? Yeah, I can talk about that. So it looks like in your method you've got sometimes too much of control which you give to the artist, which you give to the user, and that may be at some points just overwhelming. And also I feel that if you got to define which changed the control shape, well, the lattice basically, then it might be quite confusing for the user. So my question actually, have you tried your method on actual users who work in computer design to get some insights?
Actually, my work is actually, you can see that it's a enhanced version of FFD that we could provide geometric deformation, also the topological editing of the proxy during the deformation process. So maybe later can provide maybe use can be used in some software such as 3D Max or Maya, something like that.
All right, thank you.
Yeah. So, are there any other questions from the audience? I think it's the right time to conclude this session. Okay, so let's thank the two speakers, Changfeng and Yuzhe. Thank you for your talks. And yeah, let's conclude this session. Thank you.